and I am Kishore Kumar Mandal, and a very warm welcome to all for participating in today's webinar on LITE Talk and Workshop. Hope you guys are safe in home and you have enjoyed the first LITE Talk on yesterday. So before moving to the next, just give a brief overview about our organization and activity. In IIT Bombay, we run OSA and IEEE student chapter with title Photonics chapter IIT Bombay. As you know, OSA and IEEE is a reputed journal in optics and photonics field. And for the activity sessions, so we inaugurated IEEE Photonics student chapter with invited speaker Professor Pankaj K. Jha. He is from Caltech Institute of Technology, and he delivered the inaugural talk and introduced our talk. And next, apart from that, we also conducted Ask Me Anything session with two professors. First by Professor Miche Hiers. She is from Leibniz University, Germany, and another by Professor Pankaj K. Jha. This session was fully motivated and interactive with early career student and researchers, and both of them share their PhD life and experience, and also introduce the research field in more details in photonics and optics background. And apart from that, we conducted Photonics online meet, which is virtual conference for optics and photonics researcher. So the goal is to aware all the optics and photonics researcher about the new research coming on this area and give the innovative idea. So this online meet is delivered by 3 speakers as listed in here. Apart from that, as a OSA and IEEE student chapter, we organize a outreach program to encourage and motivate school level students so that they should aware about the scientific activity in day-to-day life and little bit our research field area. And we also make scientific experiment more fun and learning the experience. In future, we are planning more educative sessions at school levels to encourage the students. And coming to the main topic. So in lockdown session, we are conducting a virtual conference on LITE for innovation, thought and education, and we have successfully finished our first session, that is LITE Talk on 8 May. Hope you guys have enjoyed a lot. And this talk delivered by 3 speakers. First one by Abhin Varghese, second one by Devi Prasad, and third one by Rajeshwari. So basically in this talk covered all the building block of optics and photonics background. So and they explore about the application of this area optics and photonics in real life. So now question arises, how to fabricate or simulate photonics device or photonic integrating circuit for practical realization. So the answer you will get here in LITE workshop today. So today there will be 2 talks. First one by Mr. Vipreto Mayer. He will introduce about introduction to photonics fabrication, and second talk by Mr. Abhishek Mall. He will give an introduction about photonics modeling. So here you will get more details about fabrication and simulation of photonic device. And to reach us, you can find us in all the social media platform, Twitter, and follow in Facebook. And for more inquiry, you can mail us. For more details, you can reach us at our official website, Photonics student chapter, IIT Bombay. Now comes to the today LITE workshop talk. The talk will be on photonic device fabrication, which will be delivered by Mr. Vipreto Meyer. I will just give a brief intro of our speaker. Mr. Vipreto is a PhD scholar at CENSE, Center for Nanoscience and Engineering in IIT Bangalore. He is working under Professor Shankar K. Selvaraja at Photonic Research Laboratory. His research interests include process integration, integrated optics, and micro-optomechanical system for sensing applications. He have more than 10 plus paper research article in optics and photonics field. So let's welcome Mr. Vipreto Meyer to deliver a talk on fabrication of photonics device. Vipreto Meyer.
Yeah.
Okay, please share your screen. Okay, so a little announcement for audience. So for question and answering, raise your hand option in below. You can find it, and host will unmute your mic. Then you may have a one-to-one conversation with our speaker, or else you may text message your question in chat box. We will take care. Okay, thanks. So Mr. Vipreto, will start the talk. Okay.
Okay. Yeah. Thank you, Kishore, for the kind introduction. First of all, I would like to thank Photonics Student Chapter IIT Bombay for inviting me to speak at LITE for Innovation through an education workshop. As the speaker have introduced, I am Vipreto Meyer. I'm a PhD student at the Center for Nanoscience and Engineering, Indian Institute of Science, Bangalore. So today, the title of my presentation is on photonics device fabrication. So photonics, as we have listened, yesterday we have a nice session on the introduction to photonics. So photonics is basically the generation and manipulation of light. So it has become a very important part of our day-to-day living. For example, it is used in sensing, communication, space technology, and high-speed computing. So compared to the traditional electronic systems, why is it so different? Photonics. So photonics gives us the advantage of high bandwidth, high sensitivity, and immune to electromagnetic interference. So high bandwidth, a good example is that nowadays we have very fast internet. So that is one very good example of photonics being used in our day-to-day life. And in sensing, photonics offers some of the most sensitive techniques to measure different types of gases, chemicals, and also the last point is that it is all these photonic device it is immune to electromagnetic interference. So going forward, these different applications are achieved by combining these different optical components. So for achieving this, the requirements, we need a laser source, a kind of diffraction grating. So these diffraction gratings are used to separate out different colors of light. And if you want to filter a single wavelength of light or a color of light, you can use optical filters. Or if you want to measure the intensity of light or the power of light, you can either use a detector. So these different discrete components can be combined to meet a specific requirement or an application. So if you combine all these things, since they are discrete, it becomes a very big device overall. So and again, since you have to buy it separately, so it becomes more expensive. So the question comes: can we make it smaller, or can we make it more cost effective? So one way is yes. The answer is yes. So one way to do it is to use photonic integrated circuits. So photonic integrated circuit is a technology that offers integration of various optical components and or optical functionalities on a single chip, taking the advantage of micro and nano fabrication. So here in the figure, I'm showing an example of photonic circuits. So using a photonic circuit, you can divide power into different channels, and you can, using ring-like structures, you can filter out different colors of light. And if you want to tune this filter, you can have on-chip heaters that can be used to tune this type of filter operations. And also you can have on-chip photodetector. So similar to the electronics, where copper wires are used to conduct electrons. Here, in the same case, in the same way, here, waveguide is one of the basic building block which is used to connect different components, and also it is used to transport light. So this waveguide is a very important component for building as well as connecting different components. So another advantage this photonic integrated circuit offers is that it can be made in a wafer scale. So here's an example of a photonic integrated circuit, which is made on a wafer scale, which basically means that you can make multiple copies of photonic integrated circuits, and there's a possibility of mass fabrication. So you can print a lot of different devices in this kind of wafer. So here I'm showing a zoom view of around this section, showing that different waveguide configurations can be printed using the same technology that is used for making IC fabrication, the electronic circuit fabrication. So here I'm just showing some of the few applications, but the applications are endless. So for example, these are some of the most common applications photonic circuits are being used. So the first area is communication, sensing, and high-speed computing. So today in this talk, so I would present a brief introduction on optical waveguides. What is the criteria for the material selection? And I'll present the fabrication process flow. So in fabrication, there are two basic steps, or there are two basic processes such as optical lithography, or sorry, lithography and etching. These are the two steps which can be used to fabricate a device. So I'll explain about lithography and etching. And then for patterning photonic circuits, electron beam lithography is a very versatile tool. So it's a very versatile technique with which you can have you can print or you can pattern very fine features. So this is one of the advantages. So I'll be discussing in detail in the following. So in an optical waveguide, in the left top, I'm showing an optical fiber. So light propagates through the process of total internal reflection. So the right hand top, it's showing cross section of the optical fiber. So inside the core, which light is bouncing back and forth. That's how light propagates through an optical fiber. So one of the criteria to fulfill this is that the core refractive index should be greater than the cladding refractive index. So this is optical fibers are usually circular in nature. So the question is, can we make it on a planar substrate, something like this? So if you have a silicon dioxide bottom layer, and you have a silicon which has a refractive index of 3, and then you have air on top. So this satisfies this. So this condition of total interreflection. So in the vertical direction, light can be confined. So the question is, how can we confine in the horizontal direction? So the horizontal direction can be achieved by just removing the material on the sides. So here on the left side, the same operation or the same functionality that is there in the optical fiber can be achieved in a planar substrate also. So by defining rectangular type of structures. So here I'm showing an example of a simulation which is showing that the red color indicates that light is confined inside the silicon. So the thickness is just 220 nanometers and the width is 450 nanometers. So this indicates that devices are very small and compact. So the question comes, how do we select this material? What material is best and what material is suitable for guiding light? So the material selection, again, I'm taking the example of an electronic circuit. So in electronic circuit, copper is used because it offers the minimum resistance. So here in this, similarly in optics, so if you want to have a material which you want to transport light, so you want to have minimum absorption so that it can travel a very long distance. So it turns out that silicon and silicon dioxide is a very good material and which is transparent in the telecom regime. So it can be used for telecommunication application. Another advantage is that silicon and silicon dioxide, you can directly use the fabrication process, which is developed for IC fabrication. You can directly use to make silicon waveguides. So nowadays, silicon on insulator wafers are available. So it will come in this kind of stack. So the right hand shows an actual wafer. So the stack will look something like this, where the device is made on a thin 220 nanometer layer. So the next step is, how do we make waveguides in this kind of structure? So the fabrication, so this is the fabrication process flow. So one of the three basic steps is cleaning, lithography, and etching. Today I'll not be discussing much about cleaning, but cleaning is one of the most essential steps and is one of the most important steps. But but the take-home message for cleaning is that it removes contamination from the wafer. So it is one of the first steps that is used. So in lithography, as I've shown in the cartoon here, so lithography is a step which involves patterning of the design on an intermediate polymer film. For example, you have a design in your computer. You want to translate on your substrate. So what lithography does is that you'll fit it into a pattern generator which recognizes your design. And then through lithography, your patterns can be transferred on an intermediate polymer. So here the red thing is a polymer, a thin film polymer that is coated on the wafer. And followed by this is that the polymer is used as a mask, and then the exposed part gets removed. So that's the etching. So the etching helps in transferring the pattern on the desired substrate. So we'll have a look at lithography and etching one by one. So the first step in lithography is coating. So to get something like this. So how do we do that? So the coating is done by a process called spin coating. So in spin coating, the wafer is placed on a chuck, which is held together by vacuum. And then the solution or the polymer is being dispensed. So here in the right hand, I'm showing a figure where a person is directly pouring the polymer onto the wafer, and this is the wafer and this is the chuck. So and in order to get a very uniform coating on the surface, the wafer has been rotated at a very high speed. By this, we can achieve a very uniform and very thin layer. So basically, the photoresist is or the resist is a polymer which is sensitive to UV or electron beam. So now we have achieved this. The next step is to pattern on this. So the pattern can be achieved by either electron beam lithography. So here I'll be explaining about electron beam lithography, but there are other methods such as optical lithography by which you can do the same process. So in an electron beam lithography, the right-hand side is an actual lithography machine. So the design is being loaded on this computer, and here's the pattern generator, and then this is the electron beam lithography tool. So the design, the pattern generator recognizes your design, and then the beam is deflected according to your design. So by the deflection of the beam, you can write or pattern your desired patterns. So after the exposure is done onto the polymer, the next step is to put into a solution or a chemical, which is also known as a developer. So the exposed part will get dissolved. So this step, what we have achieved is that the design, the pattern or the design which is there in your computer gets translated on this thin intermediate polymer layer. So like I've said, the next step is etching. So what is etching? So etching is basically a subtractive method, or it's basically the removal process by which the unprotected part of the resist gets removed. So here, when you expose to a chemical, the chemical can be a chemical reaction, or it can be either be an ion bombardment. So the portion which is not protected by the resist, it will get removed. So in etching, there are two possible things that can happen. One is isotropic etching and one is anisotropic etching. So in isotropic etching, the etch rate or the removal rate is same in all the directions. So you'll end up in something like this, which is not desirable, because we want something like this, but we end up something like in a structure which looks like this. The other is anisotropic etching, where the vertical direction removal rate is faster than the horizontal. So you'll get a structure which looks similar like this. So isotropic etching happens in when you use liquid chemicals, but dry etching, anisotropic happens in a dry etching process. So the advantage of dry etching is that you can use gases. So, and by tuning the parameters, you can get an isotropic etching. So one way to achieve it is to use reactive ion etching. So reactive ion etching is a directional etching process which uses a combination of both. For example, you'll have ion bombardment and you'll have chemical reaction. So by this way, you can achieve a structure which looks something similar to this. So how do we do reactive ion etching? So reactive ion etching can be basically is a plasma etching. So you'll put your substrate in a chamber which consists of 2 electrodes, and then you'll supply a gas. So when you apply a right amount of voltage, the electrons will, the accelerated electrons will come and hit the gas molecules, and then it will ionize. So by this way, it will also generate very high reactive radicals. So when these radicals and ion comes and interacts with the surface, the unprotected part gets removed. So this is a process by which the unprotected part gets etched or removed via chemical reaction or bombardment. So, so this is the complete process step by which the intended design which is there in your computer gets transferred on your substrate. But this is not the end of the story. So some of the problems that you can face. So the intended design is something like that, but in the actual, you might get something like this. So discontinuity or roughness. So discontinuity, so since light propagates through the process of total intersection, this kind of discontinuity, light may leak out. So at this kind of junction. So this is not something it should be avoided while making your making a photonic integrated circuit. So where does this come from? This kind of errors. So basically, it comes from the patterning. So let's look at the patterning technology techniques. Let's have a closer look at the techniques. So basically, one of the most common patterning technique is the area mode patterning, which is also known as deflection of electron beam. Or so by what I mean by that is that the electron beam is being deflected, and then you get the patterning. So let me play it once more. So you have this electron source, and you deflect the beam, and then you get this kind of structure. But in a photonic integrated circuit, these devices are quite long, and it covers a large area. So, but this deflection, the electron has a limited range. So how do we write this long circuit, or which covers over a large area? One way to do it is to divide this area into small boxes, which is also known as right field. And you can deflect the electron beam in a small area, and then you can move the stage and then you can write this, and then you can write the complete area. But the problem is here is that as you keep on writing over time, the stage uh, has some drift over time because of the noises in the tool. So this kind of noises and results into a misalignment in within this two area or this area. So as a result, this is a very common problem that you'll face in area mode writing, where you'll have this kind of discontinuity. So stitching error, as we have discussed in the previous slide, it results into high optical losses. So how do we avoid this? So in order to avoid this, one way to achieve it is to use a method called fixed beam moving stage. So as the name suggests, you fix the beam and then you just move the stage. So by this way, you can eliminate stitching error, and you can write a stitching error free over a large area. So this will completely eliminate that the problem that we had in the previous slide. So let's look closely at the photonic integrated circuit. So as I explained in the first slide, photonic integrated circuit waveguide connects different components, but different components does not necessarily mean that all the width will be uniform. So in order to efficiently connect or couple light from one width to another width, there's something called taper, which is basically a varying type of structure. So by this kind of structure, you can connect two different widths. So basically, what I mean is that you can efficiently couple light from one system to another system. So this is very important for making a very efficient photonic circuit. So can we write with this FBMS structure? So the answer is no. You can write this, but you cannot write this. So this limitation comes from the tool. So the FBMS does not allow that. So to overcome this, one way is to use a combination of both FBMS and area. So you write the taper area using an area mode, and then you connect that. But again, the problem is that the stage drifts over time, as I have explained in the previous slide. So you'll end up in something like this. So you'll have some alignment error at the overlap region between FBMS and area. So we have come up with a technique, which is FBMS tapering technique. So in this way, all the circuit is written using only FBMS. So the larger widths are written by combining multiple FBMS paths, and as you come closer, you fix both the paths to a common point. In the process, you form a tapered-like structure. So here is an actual SEM image, which is showing that this kind of discontinuity on the left-hand side is completely eliminated. So by this way, you can achieve a very smooth and alignment error-free patterning using FBMS only. So here is an example which I'm about to show. So here on the bottom right, I'm trying to I'll try to explain how to achieve this kind of structure. So where you would like to pattern a tapered structure and a waveguide and a corrugating structure, which is also known as a grating. So the process is similar. So you start off with an SOI wafer, which here the brown color indicates silicon, and blue is silicon dioxide. So the first step is to do coat and do electron beam lithography. So this is after you pattern and then develop. So the exposed part gets removed in the developer, and the next step is to do etching. So in the etching, you put inside an RI, and the complete silicon gets removed. So in this portion, silicon gets removed. So and you time it in such a way that once it's when it reaches silicon dioxide, you turn off the process. So, so the waveguide, this part is achieved. So the next step is to pattern these corrugating structures. So in order to do that, we do another e-beam lithography where we define, we pattern only in this portion. So here in this case, after patterning this and putting in the developer solution, this part gets removed or dissolved. So and then you do another RIE, and then you remove the uh, photoresist. So this is a complete process flow for making a waveguide and the coupling structures. So by following the same procedure, we made fabricated photonic integrated circuits. So here I'm showing a Y splitter where this kind of structures can be used different, it can be used to split light, and then this kind of wire to slot is used to combine light into a single waveguide. So in summary, I have explained about the material what is the criteria for selection for the criteria for selecting a waveguide material, which is based on the transparency, and then lithography and etching can be combined to pattern to transfer a pattern on a substrate. And then we have explained about fixed beam moving state patterning technique, which eliminates stitching error. And then finally, I have presented about a patterning method, which by using only FBMS. So I'd like to thank organizers and my colleagues at IIT Bangalore for. So this is my group, and then this is our clean room where we are doing our experiments. Thank you for your kind attention.
Okay, thanks, Mr. Viprato, for introducing and exploring the fabrication technique from basic to sophisticated CMOS technique that involved in photonic device fabrication by step. Now move to the question answer session. So audience, please raise your hand and ask the question in chat box. Dear audience, any doubt, any questions? One question, how efficient is electron beam lithography for 3D fabrication? Mr. Viprato, please explain.
Electron beam lithography, it's a planar technique. So for 3D, as far as what you can achieve is just a planar device. And what I mean to say is that you cannot make 3D structures. So 3D structure you would need. So what you do is you pattern one structure, and on top of that you deposit another structure. So by that way you have to do multiple alignments. So that is something you have to do. But electron beam is as such, it's very precise, and you can, as long as you can identify what is beneath in the bottom layer, you can always do 3D types of patterning. I hope that answers your question.
Okay, so one thing I will include in this question. So for 3D fabrication, so I would suggest go for the 3D laser lithography. That is more efficient than electron beam lithography, which is very fast to write the patterns as compared to electron beam lithography.
Yeah, correct. Yes. Yeah. Thanks.
Come to the next question. Is from CV. What are the difference in fabrication process of MEMS sensor and optical sensor? Mr. Viprato.
So in MEMS sensors, optical sensors, you can make it without any moving parts, but in MEMS sensors, uh, you need some kind of moving parts. For example, you need to have a cantilever or something like that. So the you use the same process, but again, the tool, say etching, everything is same, but you tune it in such a way that you either make a structure which is not movable, or so the only difference is that in MEMS you will have some part which will be moving. So the principle is different. So the fabrication is slightly different. So I think that's the basic difference. For example, in, uh, in optical sensor, you just need a waveguide. That's all. But in MEMS, you need some kind of suspended structures like cantilever or accelerometer. So it has to be hanging on some anchor or something like that. So that's the primary difference.
Okay, thanks for explaining. Another question is, can you talk more on negative and positive photoresist? I think
Okay. Yeah.
this question is very preliminary, so you
Yeah.
can get it from just Google search and all. So please give a brief overview about it.
Yeah. I'm not sure whether I can use a pen or something. So I'll just try to draw it here. So in a positive resist, so if this is the electron beam, if you expose this part, and if this is negative resist, if you expose this part, so after development, you put into the solution, what you will end up is that you'll end up something like this. But in the negative resist, you will end up something like this. So so in this case, what happens is that when you expose this polymer, the polymer starts breaking, and then it gets dissolved in the solution. In the negative part, when you expose with an electron beam, the polymer linkage starts happen. So it becomes more resistant to the solution. So the other parts gets dissolved, and this part remains. So this is the primary difference between positive and negative resist.
Okay, thanks for your explanation. Any more question, audience, please? Okay, so we are not getting any more question. Okay, we are running time late. So next, move to the next talk. So let's thank Mr. Viprito for excellent talk on device fabrication. Now handing to Mr. Anush to introduce the next speaker for delivering the talk on introduction to simulation on photonic device fabrication. Mr. Anush.
Thanks, Kishore. So, in this series, our next speaker is Mr. Abhishek Mal. So, Abhishek did his undergraduate from Hansraj College, University of Delhi. After that, he joins Bombay as a MS Tech degree student. Presently, he is working in Laboratory of Optics and Materials, Department of Physics, IIT Bombay, under Professor Ansuman. So Abhishek is going to deliver the talk on introduction to photonics modeling. Abhishek, please can you share your screen and start the talk? Abhishek.
Yeah, okay. Thank you, Anuj. I will.
Yeah, okay.
Okay.
Please
I
share
will
your
share my
screen.
screen. Yeah. Everyone can hear me?
Yeah, you
Yeah.
can
Good
start.
afternoon, everyone. So I'm Abhishek Mal. I am final year master student working in Laboratory of Quantum Optics of Quantum Materials, Department of Physics, IITB. So today I will be discussing about modeling in nanophotonics, which is majorly the discussion over what are the tools which we use while understanding the nanophotonic devices before going for the fabrication process. So here I will start my discussion with this outline where I will include few introduction about the light modulation techniques, which will discuss what how we can modulate the light over by using different kind of materials and nano patterning on the structures, which will include discussion over metamaterials and meta surfaces. Then I will move to simulation methods, which will include why simulation is important and how, what are the types of methods which have been introduced up till now and how effective they are. And while doing some theoretical analysis, which kind of method we can choose. Then I will discuss a simple example of one of the modeling methods, and then move to a new modeling approach. Then at the end, I will discuss about my work, which and the simulation methods I've been using. So let's start. So light modulation is a very intriguing phenomena where you try to modulate the intensity or state of polarization, amplitude, or phase of the light. So these are mainly achieved by using materials called metamaterials or surfaces, which are materials with artificial properties. So these artificial properties arises due to the structure of the material rather than the intrinsic property. So mostly it arises because of the topology, the way you tailor these dimensions, which could be in subwavelength scales. So for a visible range, that could be around few of hundreds of nanometers. So here, for a as an example, we have polarization detection. So meta surfaces are used as a sandwich structure where metal dielectric metal is uh, used for polarization detection. For a normal incident can be separated into different state of polarization. Then moving on, we can also have meta surfaces and metamaterials used for beam splitting also, where an incident light could be used to split the beam into the different polarization states by introducing some phase difference between both the orthogonal components of the incident light. Then we can also have some phase and amplitude control together, where we try to pattern small structures in different orientations. These orientations introduce a phase gradient into the reflected beam light, and these phase gradient can be designed according to the orientation and the size of the nano antenna. So here in the left bottom image, you can see the silicon patterning, where the orientation and thickness introduces different kind of phases into the incident beam, and then in the reflected form we find a optical vortex with the intensity varying from center to the edge of the vortex. Then again, we also have different sizes of these nanostructures. Instead of having just rectangles, you can have meta atoms or meta molecules, where you can have two structures or three structures in a single unit cell. So these also changing the dimension in a single unit also introduces some kind of phase and amplitude modulation into the reflected beam, which can be used for vortex beam splitting, polarization detection at the same time. Then also meta surfaces have been used for enhancing the efficiency of other devices, which could be based on photo detectors or modulations of the uh, signals in optical fibers or holographic imaging. So in all the three cases, we have different type of interaction of meta surface with different devices. In the first case, meta surface patterning, which is snowflake like structure, which introduces and couples with the graphene layer, and introduce a strong plasmonic coupling, which increases the response of the graphene absorption response of the graphene. Secondly, then we have the signal modulation, where you can have a meta surface patterning, which can control the propagation of light in either of the direction. So in this optical fiber, you can have NOR gate and gate functionalities by absorption, reflection, or full transmission of the light in either of the directions. And then we have holographic imaging, where you pattern different antennas at a flake, where all those antenna dimension introduces a phase, and those phases uh, constructively interfere or destructively to give rise to an imaging pattern. So these kind of applications makes it intriguing to know how the light is interacting with the matter at sub-wavelength scale, and to understand these kind of interaction without directly going to the fabrication, we need to understand the working principles of electromagnetic interactions at these levels. So here comes the simulation part, where we try to model those systems and try to see what kind of understanding we can take out before going into the fabrication. So what a typical definition of simulation is: designing a model of the real system to understand the behavior and evaluate the system basis of the response or the desired which we want from our desired system. So these could be narrowed down into simple points of understanding the bottleneck of the problem, where you could have a device where you want to push its limits to a better efficiency, or you want to have a device where you want to see its responses to different configuration changes. That could be some thermal changes, pressure changes. You want to measure the device under different environmental conditions, or you can have some dynamical changes where the external components could be the gate voltages and the temperature and doping levels, which you change drastically into the system, and how you want to see how these changes are affecting the response of the system. And then you can also have the situation where you want to find the equilibrium state of the system, where you would have the optimum responses with the highest efficiency, or the highest coupling, or any of those functionality which you want at a very without any disturbance from the external environment. So all these narrow down to one important point, is that design and analysis of these fabricatable systems before you need to do all these bottleneck responses thing. So when we in the meta surfaces and meta materials for these designs and analysis, what we do is we do the optimization of the device. And these optimizations are mostly related to the topology optimization, where you try to optimize the size dimensions of the device and try to see how the response of the device changes by tailoring them. So while doing this, we try to adapt some modeling methods in these nanophotonic systems, which are typically based on solving these four Maxwell's equations. So what we do is we try to solve in different scenarios these different equations and try to see how the system is responding. So the first method is finite element method, where what it does is it divides the whole system into the small elements, and these elements are uh, uh, are used to calculate the response of the system at the level where you have approximation very closer to the accurate responses. So it can be done in a way that, suppose you are solving for the bottom two Maxwell's equations. So this finite element method, what it does is, for a particular element, it solves the Maxwell's equation at two nodal points and try to see the approximations and at those points. But the good point here is that the smaller the element size is, that the better the approximation, but it increases the computational time drastically. So we have to be very careful about choosing these elements while performing these simulation and solving the Maxwell's equations. Then the next method is using finite difference time domain method, where you only solve for the bottom two Maxwell's equations. Why we try to solve here these curl equation is because we want to see the progress of the solutions of our Maxwell's equation in time domain as well as in the space domain. So what we do is we perform the discretizations of the time and as well as the space. So a simplest example would be a one dimension device, where you want to solve the Maxwell's equation, where you have, suppose, a z component polarization incident, and then the curl equation turns out to be in these two simpler equations. And when you solve these equations in the discretization format, you end up with these space and time discretization, where delta x and delta t are the discrete elements in the space and time, and the m and q are the units of those elements, which completes the whole system. So while solving these finite difference time domain equations, the algorithm works in a way that you know a previous solution, then the next solution is computed on the basis of the previous solution, and this cycles repeats till all the solutions are evaluated. Then we have another kind of modeling systems which uses evolutionary algorithms and genetic algorithms, where you try to minimize the function. The function is the combinations of some desired functionality, where you could have phases and the amplitude. Now minimizing a function means that you are trying to find the optimal minima or maxima for that function, such that while tailoring the parameters p of the geometry, you get the highest response of the phase or the amplitude by minimizing those functions. These algorithms are very helpful while you have large parameter space for a specific geometry, but when you want to transition to different geometrical designs, these evolutionary algorithms get iteratively expensive. Also, you need to have a previous knowledge about what is the nature of your functionality or the target response. Here we are talking about the phase and the amplitude, that for a certain situation you could have an amplitude of unit, or you want an amplitude which should be varying as a Gaussian. So knowing these previous knowledge, you need to choose precisely those minimizing functions so that you get the optimal parameters. So those are evolutionary and genetic algorithms which can come in handy while optimizing for a particular geometry. But moving on, recently a focus has been transitioned towards the deep learning methods, where we use deep learning neural networks to learn these mm, uh, Maxwell's mapping or solutions between topology and the response, so that we have the desired geometrical designs for the particular desired responses. So how this works is that in the same way the finite element, finite domain, or evolutionary methods work, they try to go from geometric space to the response space, where you try to optimize geometry, run the simulations iteratively, and get the desired optical response. And you tailor to the point such that you get the most efficient response you desire. But in the deep learning, you do it the different way. Here you try to give the desired response, and the deep learning method will try to find those optimized parameters for you. So the one method is trying to use two concatenated networks, where there is a forward network and a reverse network. What forward network does is uses design parameters D and learns the mapping between design and response. So this is a forward design which is totally followed in all FEM FDD evolutionary strategies. While in reverse design, what you do is you want to give a response, a desired response, which could be anything, phase, amplitude, or the efficiency, and you want to get the desired geometry. So this happens is that you need a starting data set solution on which the machine learning algorithm learns and try to map that. And once the machine learning algorithm has learned efficiently, you give the desired responses and you get the predicted desired geometry. So the only difference here is that the only computational simulations which you use in the FEM FTT is used as a training data set for the deep learning methods. Now moving on for the FTDT and FEM packages, we have some softwares out there which uses these concepts. We have numerical FTDT software packages and COMSOL multiphysics FEM. Both the packages works just differently on different methods of optimization, but the interface and the functionality is more or less the same. Only the background algorithm working is different. So it more or less you will get, if you get acquainted with one of those packages, it's easier to get acquainted with another one. So here I will start with discussing a simple example from the COMSOL multiphysics, how you set up a simulation, what are the steps important in those simulation processes. So here's a simple window of COMSOL multiphysics, where you will see there are different uh, panels in which you can choose different options for your simulation processes. The topmost panel is the add-ons, where you can add different kind of elements to your simulation process, which includes adding a material or the type of physics you want to solve. It could be solving for semiconductors or the plasma, or you can solve for the radio frequencies regimes also. And then you can also have some external after simulation nodes, where you can add the plots, or export the results to see how the results have been due to your simulation processes. Now then you have a model setup also, where you set up all your model with the initial parameters, materials, geometry, and the physics defined. And then you get, after the running the simulation, you get the results. And then the third element is the model window, where you can observe your geometry, the meshing, and the output results. So here is an example. So in setting up a simulation, the first task is to set up the parameters and the variables required for your simulation processes. These could be defining the frequencies, the geometrical parameters, or unit cell size, these kind of constant parameter which you will be using in your simulation, or the variables where you could have a situation where you want to define the material as a surface conductivity or a function of some electric field or magnetic field calculated, uh, and then you can have the geometry setup. Once you have set up the geometry, you could have different assumptions where you could have PML layers at the top and bottom, semi-infinite substrate. You can define the meshing over the geometry, size of the geometries, and other things. And you can choose the scale of the geometry depending upon in what length scale you are working. Then you can define the materials. So the third step is materials, where you can choose the built-in materials, or you could have a situations where the materials itself have varying refractive indices, permittivity, depending upon the wavelength range you are working in. Some materials like silicon has varying refractive index in visible region. Some materials like hyperbolic materials have varying permittivity as a tensor. So you can do all those stuff while importing these materials or defining your own materials. Then you have the meshing, which typically defines how your algorithm is going to work, at what points it's going to calculate, and how closer your approximation should be. So the smaller the size of these elements, the closer the approximations are, but the simulation times get exponentially increased due to these meshing. So the alternative method is you define the regions where you want to calculate the regions where the most important coupling or the interactions are happening, and with the you can increase the meshing high there, and at the other regions you can have a lower meshing so as to compensate between the computational time. Then you can have setting up the physics study, where you can define different periodic conditions, scattering conditions, and define the ports, where you can define where is the uh, source and the detector, where you calculate all the fields. And then different wave electric equation, where you have perfect electrical conductor situation, or different domains where you can define different physics also. So then the comes up the final step of running the simulation and analyzing the result. So mostly there could be situation where you want to run for a particular frequency or ranges of frequency, and then you can analyze the result by looking at the field profiles and the corresponding reflection spectrums. So now, after doing all the simulation method, one thing which was understood, that with increase in complexity of the nanostructures, the simulation time increases. So deep learning has been introduced as the alternative for understanding the modeling of these nanophotonic structure for their topology and their corresponding responses. So if you have a simple single resonance device, then you could have simple analytical modeling, or then with increasing the complexity of the response, you increase the modeling setups, which goes from semi-analytical to FEM FTDT methods. But when the complexity increases, where you have multiple materials, multiple topologies, or you want to find such topologies for that the desired responses are achievable, but requires high complex simulations and solving of Maxwell's equation, then you can it gets very complicated to solve those equations. So here we introduce, people have been using the deep learning methods, and these deep learning methods have been successful in comparison to the FTT simulation, where you can see that a particular full wave simulation could take hours or days in some scenarios, but full trained machine learning model can generate the optical response and a desired topology for a desired response in few seconds. So emphasizing on that, we have some recent works where people have introduced different machine learning models for desired input optical responses and uh, corresponding predictions of the geometries. Here we can see that the people the in this paper, the H-shaped geometry has been optimized, where the variables could be the length L0, L1, and phi angle, and omission of the length. So how this machine learning algorithm works is, you have a two fully connected concatenated networks, where there is a forward network which goes from geometry to responses, and there is an inverse network which goes from responses to the geometries. So what you do is, you first train your model on the simulations data set for the forward network, where it maps from topology to the responses, and then you have the inverse network which maps from the desired responses to the topology of the nanophotonic devices. So it is very difficult to train the inverse design because there are certain problems. The first one is the non-uniqueness, where you could have two designs or more than two designs for a particular desired optical response. So for those situations, the machine learning models becomes very hard to converge. So that's where we have the forward design models which guides the reverse model to a particular solution. So that's why it bypasses the problem of non-uniqueness. So in the plots, you can see that after the full training, if you give in a desired response, the predicted response are quite closer, and the predicted geometry by the deep learning method is quite comparable when you do the fabrication and get the optical response. Very successful map these optical responses to the geometry to the optical responses uh, functionalities. So this is for a particular geometry where you already have a geometry in mind which you want to optimize. But suppose there could be scenarios where you want to generate new geometries for a desired optical response. So that's where the generative models have been used, where they understand the geometric space and the response space as a probabilistic distribution, and due to this probabilistic distribution they generate new designs for a desired optical response. So in this example, you can see that the ground truth, which is the original design, was a star shape, and then the generated designs were a spherical shape, but the responses from both the designs are similar, which means that even if you have some complicated geometries and you have corresponding optical responses, these generative models can generate simple geometries which will have similar optical responses, and is a very good method to eradicate the fabrication limits, where you cannot generate, as discussed earlier, that the if the geometry gets complicated, it is very limiting to fabricate all those geometries. So moving towards that, after the optimization and the design, people have also used machine learning models for understanding the underlying physics also, where they have done a dipole resonance engineering, where you input the desired electric and magnetic dipole uh, resonance extension spectra, and you get the corresponding materials which can be used to get those desired optical responses. So instead of choosing those materials and the dimensions of those materials, you directly give in the desired responses and you get the desired topology, and then you can do the fabrication onward. So in a sense, while training on a simulation data, deep learning models are very successful in mapping those relations and understanding them as a full model of electromagnetic wave equations, and then giving us the topology for a desired uh, uh, electrical responses, which could be phase amplitude. In this case, we have electric dipole and magnetic dipole as extension spectra. So on that line, I've been also working on those kind of methods using deep learning for the optimization and inverse design. So here what we try to solve is that how we can have a single optimized machine learning model for optimizing multiple geometries at a single run. So what we do is, for the forward simulation, we generate a data set where we have different topologies which have corresponding responses, and then we train our deep learning model. So we train our deep learning model for mapping of forward responses and the inverse responses. So in the inverse response case, you could have one-to-many mapping, where you could have a particular response, and then for those responses you could have different geometries. So what it does is, in our method, we train our network such that it searches for those geometries which have closest responses by searching into the geometric space library created by our forward network, which learns the mapping from topology to designs. So in such a manner, it eradicates the need of training multiple models at the same time, as we have seen in the previous cases, where you have a forward design deep learning model and the inverse design model. And also we eradicate the need of the issue of the convergence, where we, instead of uh, our machine learning model going to non-convergence, it searches for the closest designs, such that in a error window we get the closest optimized design parameters. So in at the end, I would like to conclude with the discussion that there have been different developments in the methods of modeling to decrease the iterative iterative methods to optimize optimized limits so that we have less simulation time, but with the desired optical responses. But to further reduce that, we have also people have also introduced and come up with deep learning approaches to replace these conventional approaches. And for the further future aspect, we can also have areas where we can in parallelly use these conventional approaches of FTDT, FEM, or evolutionary algorithm together with the deep learning approaches to get a better, less time consuming, less iterative, and more precise modeling of nanophotonic designs. And that's where the gray region of deep learning and the conventional approach comes. Thank you. Any questions?
Thank you, Abhishek. For giving a wonderful talk on modeling of photonics with methods and examples, and also with few new approaches. So now the session is open for question and answer. You can raise your hand, or so I will open your mic. Otherwise, you can send a message on chat to us also. So any question and answer, audience? Uh, yeah, Abhishek, I have one question. How can we define random structures which are not available in the library?
Okay, so what happens is that when you train a machine learning model, so it learns the mapping from topology to responses and inverse design for response to topology. So if you have enough data set, so the only method to generate new design is using a generative method where it learns those distribution and try to generate new design. So to have those new designs, you should have a variability in the data set itself. So if you don't have that much variability, the machine learning model will try to converge to the known distribution which is it has learned in the design. So it will try to converge in the existing designs only. So to have new designs, you should have a variability in the data set itself.
Okay, thank you. I have one more question. What are the optical parameters you considered in your model to get a structure?
Uh, Optical parameters to in a machine learning model.
Yeah, yeah.
Yeah, so in the machine learning model, the optical parameters you could choose. It could be anything. The phase also, reflections also, and the amplitude also. So these kind of responses you can choose, which can correspond to not just the topology of the nanophotonic designs, but also the materials used for the design. So as you have seen in the example of the engineering of dipole resonance, they not only optimizes the geometry but also the materials for the desired optical response. So yeah, you can go either way. You can change the optical properties as resonance and the materials in the same way.
Okay, thank you. So one more question is there. So can we integrate scripts into the user interface? So I think yes.
Yeah.
So you
So
can explain better.
yeah, so in
Yeah.
FEM and FTDT, there are options to introduce scripts. So you need not to go through the conventional, just using the user interface. You can write your own script to do the iterative simulations, and you can define those methods to do
Okay.
the simulations.
One more question is there. Which software will be more effective in modeling 3D photonic crystals in terms of computational memory and time?
3D photonic crystal probably. So FTDT and FEM more or less are the same. So if you want to decrease the computational memory, I would go with the try to play around with the meshing of the depending upon the size of your photonic crystal. So I have seen papers with you using consoles also. So you can decrease the computational time in that sense.
Okay, so one more question is, can you suggest any open access software for perovskite simulation?
Yeah, open access you can use Meep. So it is Meep and S4 are there. So you have to do the scripting. So they provide the packages for the materials. So you can do the scripting on your own by defining the geometry and materials. So Meep is an open source. S4 is also there. So you can use these softwares. So these are it's a scripting based software. So it can be done in simply in Python.
Okay, Thank you, Abhishek. I think no more questions are there. So thank you for the wonderful talk. So now I will. So since all of you, as Kishore introduced in the beginning, we are the Photonic student chapter. Uh, Organizing this ideal event. In the ideal event, we are hosting See the Light from the Home campaign. So in this context, we have some contests as well as talks. So some student activities are over. 2 days student activities are there. So hope you all enjoyed these activities. Except that we have ideal photo contest and ideal write-up contest. So for ideal photo contest, you will send us your photo related to optics and photonics with maximum 25 character description. You can send us on this barcode, scan this barcode and send us. Otherwise, you can go for more information, you can visit on our website. For write-up contest, you can also, we have 2 topics. One is optics and photonics to fight COVID-19, and other is optics and photonics for a better living place post the COVID-19. So either one, yeah, it's not shared. No. Okay, I shared it. Are you able to see now?
Yeah.
Okay, thank you.
Go ahead.
Sorry. So we have 2 this talks. So these 2 contests we have. So this you can send us on this URL, or for more information you can visit our website. And I hope you all got the mails regarding that. And we have up to 500 prizes for both of them. So first prize is 1,000, second is 800, and third prize is 500. And except that, in the talk series, in the context of talk series, we have next talk by Professor Ajoy Ghatak and Professor Kaushik Chaudhary on 16th of May from 11 to 12:30. So for that, you guys can receive the link soon for the registration. So you can also visit our website for more information. For contact us, you can mail us on this itbphotonics@gmail.com, or you can follow us on Twitter and Facebook handles. So I hope you all enjoyed the session. So for next, I have a request to all of you. Please please on your video so that we can take a snapshot of the screen, because it's a very necessary thing in the time of social media. So please on your screens. Okay, thank you everyone for the support, and I hope you enjoyed the talk. So we'll meet on 16th again. I will send the registration link to all of you. Okay, bye. Thank you again.
Bye bye everybody.